Hello, my name is Nazeer from the Faculty of Civil Engineering Technology, and I would like to welcome all viewers across Canada and around the world. In this presentation, I am going to present couple, which is a type of moment. It's called a pure moment, and the reason why a couple is considered to be a pure moment is because if you have an object and you have different points of application, no matter where you take moments, that couple will have the same effect no matter if your point of application varies. Now, the most important thing is that we have to first know what a couple is and how to recognize a couple, right? So a couple, hence the name, there are two forces, it's a couple, and the forces have to have the same magnitude, 5 kilonewton in this case. We have to have opposite sense. The sense, as you know, is given by the arrowhead. Okay, one is going to the right and one is going to the left. We have to have parallel direction. Well, in this case, our line of action is horizontal. It has to have parallel direction, meaning that the distance between the two lines of action remains the same. No matter how far you extend them, they will remain the same. That's the definition of being parallel. When we look at the distance between them, it's a perpendicular distance between the line of action, and in this case that perpendicular distance is 2 meters. Okay, let's go and look at the equation to create the moment of a couple. It is the same moment equation, it's force times distance, but the distance in this case, because we have a couple, it's going to be the distance between the line of action. Rather, when you're doing moments about a point, it would be from the point to the line of action. In this case, it's between the two line of action of the couple. Okay, now that we know that the magnitude is 5 kilonewton and we're going to multiply it by 2 meters, so we're going to have 10 kilonewton meter, not per meter but meter. They're multiplying each other. Now when we look at the rotation now, the rotation here is going to be clockwise, and how do I know that? I'm going to join these arrows head to tail, right? Head to tail. It still gives me clockwise rotation. As we know, clockwise rotation is considered to be a negative rotation. Okay, so we know how to recognize a couple. We know how to calculate the moment for a couple. We know that the moment from a couple, no matter on the entire plane, it'll have the same effect. Let's go to another problem, and this is more of a realistic problem that you would see in statics and strength of material. We have a mass, and it's 1,000 kilogram. We're going to have to change this into a force, and we have several angular forces. We're going to have to resolve that to their horizontal and vertical components. We also have this particular force here and this one. And as we have I have described in the previous slide, same magnitude, we have opposite sense, we have parallel direction, and we have a space, perpendicular distance between the line of action. This line of action is like an arrow shoots. This one is the same thing. Okay, that's the way that force works. Forces are vectors. They have to have their 4 component: magnitude, direction, sense, and point of application. Now we are asked to find summation forces in the x direction, y direction, and summation moments, and that's where I'm going to stop with this problem, meaning that you could do summation moments about B and C. I'm just going to do summation moments about A, so you have an idea of how to go about doing summation moments of B and C. Like I mentioned, we have to resolve these forces first. We have to convert this particular mass into a force, and we're going to work with the couple that we have here. The first force that I'm resolving means that you're going to solve for the horizontal and vertical components. You're going to do, it's basically a right triangle that you're solving. When we look at this, the horizontal component is going to be 10.6 kilonewtons, and it'll be going to the left. this main force here, the only way that these components could have the same effect as the main force is if this one is going to the left, the horizontal is going to the left, and the vertical is going down. Okay, so we could see that those ones are resolved. You're going to have to use solving a right triangle to get these numbers. Okay, let's go and resolve the second one. And as you could see, this one is going up and to the left. So we have the horizontal component going to the left and the vertical component going up. I'm going to resolve that. It becomes, for the horizontal, 2.43 kilonewtons, and for the vertical, 9.70 kilonewtons. Let's go and convert the mass into a force. Now, you should know that if you take kilograms and multiply it by the acceleration of gravity, which is 9.81 meters per second squared, you will get newtons. So if I were to take 1,000 times 9.81 meters per second squared, but I don't want newtons, I want kilonewtons, so I'm going to divide it by 9.81. I'm going to get, or divide it by 1,000, and I'll get 9.81 kilonewtons of the magnitude of this force. Okay? The next force that I'll resolve is this angular one up in the right hand corner here, and that will resolve to the horizontal being 21.8 kilonewtons and 31.1 kilonewtons for the vertical. As you could see, this one is acting down and to the left. Horizontal is going to the left and vertical is going down. We have one more to resolve here, and those ones are 16.6 kilonewton acting down and 6.92 going to the right. Okay, so we have resolved our forces. We have to deal with these couples though. Okay, remember we recognize these as couples. To work out the moment of a couple, it's going to be the force times the perpendicular distance to the line of action. 1, 2, 3 times 16 is 48. Okay, rotation is like that, so it's clockwise rotation. Now you notice I put I've crossed out these forces. The reason for that is that when I'm doing summation forces in the y direction, because these have the same magnitude and opposite sense, they're going opposite to each other, they will cancel out each other, so I don't have to include them in my summation of forces in the y direction. Okay? Let's go and start to do some calculations with this. I'm going to do summation of forces in the x direction first. Okay, when we look in the x direction, we have 1, 2, 3, and 4 forces. So we're going to have 1, 2, 3, and 4 terms. Terms are separated by minus and plus sign. So I have 4 terms. It's important that you have your sign convention. Summation of forces in the x direction, forces acting to the right, is going to be considered as positive. Okay, when we add these forces, 10.6, 2.43, 6.92, and this one up here, 21.8, when we add them up, we get a minus 27.9 kilonewton, right? The minus, it means that it's going opposite to this, right? If it was plus, then it would go in the direction that we dictate as being plus. Because this is minus, it's going in the opposite to that sign convention. Now, we don't have to leave the minus sign. We use a sign convention because we are adding forces. Once we have the answer, we could take away that minus sign. This is the important thing, that you get the sense correct, right? It is going to the left. Let's go and do summation forces in the y direction. When we look at what we have in the y, 1, 2, 3, 4, and 5. So we're going to have 5 terms. Remember, the couple will cancel out each other, so we're not going to include them in our calculation. We know that they're going to cancel out each other. And likewise, our sign convention says any force that's acting up is going to be positive. Therefore, any force acting down will be negative. This will be a negative force, minus 22.7. This one will be a positive 9.70, and we're going to have 16.6 in a negative direction, and 31.1 in a negative direction, and then 9.81 in a negative direction. When we sum that, we're going to get 70.5 kilonewton meter, and that is in a negative direction. It'll be minus 70.5. Okay, minus 70.5. So when you add that up, I took out the sign from this one because once I have the cents here, I don't need that sign anymore. This is my final answer. The last thing that we're going to do with this particular problem, we are going to do summation of moments about point A, okay, in respect to point A. Remember that a moment or a couple has the same moment no matter where. If I did moments about here, this couple would have the same 48 kilonewton acting in the clockwise direction. And if I did it at C, it would have the same. So it's a pure moment, it's a couple. We got to keep that in mind as we go through this problem. Okay, when we look at point A, we know that we're going to have two moments created here, two there, one from this one. We're going to have two there, and one from the couple. Okay, one from the couple. Now let's go and deal with this. I'm going to start with 10.6, and the distance from point A, if you check the grid, it's going to be 7. Okay, 10.8 multiplied by 7 will give you the moment for that particular force, and it will be taking you counterclockwise. So it's going to be a minus direction. 10.6 times 7 minus. The vertical one now, 22.7. When we look at the perpendicular distance to the line of action, right in here, it's going to be 1. And which way will this take that particular rotate that? It's going to rotate it in a counterclockwise direction. So the counterclockwise, according to this sign convention, is positive. So then we have a positive there, 22.7 times 1. Okay, let's move on to the next force, which is 2.43 times a distance of 6. This one was 7, this one will be 6. When you look at the distance to the line of action, the line of action is across here, so that distance there will be 6 in this case. So we have 2.43 times 6. And what is our rotation? It'll be a negative rotation. It'll turn that point in that direction. So we have minus 2.43 times 6. And for the vertical, we will do 9.70, and to that line of action will be 2. It'll be going positive. 9.70 times 2, going in the positive direction. When we look at the next one up, and that would be this force here, 9.81. We could check it's fairly easy to check this one, 1, 2, 3 to the line of action, and that will be taking this point in a clockwise direction, which is negative. So 9.81 times 3 minus direction, 9.81 times 3. The next one is 6.92 times the distance of 1, 2, 3, 4, and 5. 6.92 times 5. You have to ask yourself, which way, if you had a lever off of here and this force was pushing it, which way would it turn that point? It would be going counterclockwise, and we have 9.82, and where are we? 9.8 or 6.92 times 5 in the positive direction. We're going to go for the vertical now. The vertical is 16.6, and we know that it's going to take us in the negative, which is clockwise direction. We have to count the distance from the line of action to the point of application. 1, 2, 3, 4, 5, 6, 7. So we have 7 in the minus direction. Let's go to 21.8. Okay, 21.8 right here. And that has a distance of 2 from the line of action going in the positive direction, right there. And the vertical, 31.1, the distance will be 2, 4, 6, 8, 9. So we have a distance of 9. It's going in the negative direction or clockwise direction, right there. And the last thing that we have, it is the 48 kilonewton meter. Well, once you have kilonewton meter, you have a moment already, so you don't have to multiply by any distance. So I'm going to put that as 48 kilonewton meter. Because the rotation is clockwise, it's going to have a minus in front of it. And we're going to summate those forces. We're going to have a minus number, which means it's acting opposite to our sign convention. And that's why it is acting clockwise. Okay, so summation moments about point A is summated to be this number. It has a turning force, kilonewton meter, of that much in clockwise direction. I think that's it for that particular problem. Let's look at this now. Anytime that you see a force represented like this, you have to know it is the result of a couple. It's a pure moment. Okay, you have counterclockwise rotation and clockwise rotation. Okay, let's look at another problem. And this one is asking us to find x, y, and m summation moments about point A again. Now, when we examine this particular problem, we see that we have the effect of two couples already, and they've given us the actual moments of this. The other thing that I see, 20 and 20, I recognize these as moments. I recognize these two as moments. Now, with angular forces, 45 and 45, I could see that. 17, 17. These are couples too, but with angular forces, we have to resolve them. So let's go and resolve them. Okay, there they're resolved. As you could see, this and this makes one pair of couple, and this makes one pair of couples. Okay, let's go and as we know, if we were to add, because in the horizontal direction, this and this would cancel out each other. This one and this one would cancel out each other. And that's all the horizontal forces we have. So we know summation forces in the horizontal direction is going to equal 0. Let's look in the vertical direction now. This and this will cancel out. This and this will cancel out. And we have no other vertical force. So in the vertical direction also, we're going to have 0 as our summation. We have to write it down because, when you're marking this stuff, you can't take assumption. You can't make assumption about knowledge. So you have to write it down as a student. Let's go and do some calculations now, I suppose. And we're going to use this moment and this moment. And I'm going to take the magnitude times 1, 2, 3. 11 times 3 is 33. I'm going to take the head to tail direction. It seems to be going into the clockwise direction. I'm going to put that moment here. I could put it anywhere on this plane, but I'm going to put it close to the couple that actually created that moment. Okay, let's go and do another one. These two couples, and we see that we have 20. 1, 2, 3, 4, 5 so that'll give us 100. And if I go head to tail again, I have clockwise direction, hence the clockwise direction there. Let's go and deal with the other two. We see we have a horizontal here and a horizontal there. 12 times 1, 2, 3, 4. 12 4 is 48 kilonewton meter. And if I were to join these head to tail, I would have counterclockwise direction, which is the positive direction. We have the other two couple, the vertical couple, and we have a magnitude of 12. 1, 2, 3, 4, 5. That makes 12 times 5 is 60 kilonewton meter. If I were to join this head to tail, I would have a counterclockwise rotation. Okay? I think that's all that we could do to simplify the problem. We have to go and do our calculations now. We already know that summation forces in the x direction, all of the forces are going to cancel out. Summation forces in the y direction, all of the forces are going to cancel out. Summation moments, it's going to be a little bit different. We have 48 kilonewton going in the positive direction, which is counterclockwise. We have 60 right here, positive direction again. We have 100 right there, negative direction. The negative sign is right there. We have 33, negative direction, which is the clockwise direction. It is reflected right here. And we have 80. Okay, where's our 80? Right there. And that is going in the negative direction also. And we have 64 in a positive. So we have all the moments involved here in these terms. Okay, we're going to sum them, and I'm going to get a minus 41.0 kilonewton meter. Because it's minus, it's going opposite to my sign convention. Guess what? It will be going clockwise. And that's all there is to it. Thank you for watching.